So normally, like in engineering drawings, if you do a thick line in plan view, that refers to like a steel beam, okay? Depending on how much detail you want to draw. Yeah, so you've got a thick line, and then coming off of it, you have another thick line. So this would be like a secondary beam, for example. I've actually drawn it so that the secondary beam looks chunkier than the primary beam, which could be the case sometimes, but maybe I should have drawn it so that this one was thicker. But this is like the notation. And do you see how it ends here? That line stops right there. Oh, sorry, that line stops like right there. That denotes like a pin connection, which means like if I was to draw this section, let's call it section 1-1, that might be a primary beam. So this is section 1-1. And then just a recap from before, this might have some kind of stiffener plate on it. And then what you might do is you can taper your, sorry, not taper, you can cope the flanges of your secondary beam, like that, right? So that's your secondary beam coming off, and then you might add some bolts like this, right? And then how you draw bolts actually is you do like a plus sign like that to indicate that they're bolts. And then this dashed line indicates something's behind there. So that line represents the edge of the stiffener, right? And then that like kind of fillet thing is your coping. So we've removed part of the portion of the flange and portion of the web there, so that these can attach nicely, right? So that would be like a pin connection, there to there. Okay. So what I'm going to challenge you guys to do is think about what a moment connection looks like. Okay, so I'll give you an example. What I want to challenge you guys to do, right, is in plan view, let's just say you have a cantilever, right? You have a cantilever, so that's a break line. That's another break line, that way.
Plan view is top down.
Yep. This is top down. Okay, so that's cantilevering. Therefore, there needs to be a moment connection here, okay? So that dashed line thingy is basically saying, I want you to draw that detail, plan view detail, and then later once we've gone through that, so maybe we'll do like that. I want you to draw elevation detail, section 2-2. Okay, so I want you to draw the detail, top down first, and then the elevation thing. Think about what this needs to look like so that it can resist those rotational forces. Because this currently doesn't resist any rotation, like on paper, right? Like from a mathematical point of view, all right? So you guys just give that a go.
So the scenario is here. We've got a wall here, and then an I-beam cantilevering outwards, and then there's a drawing connection for that.
During the cross section, yeah. Because basically, if you have an I-beam like this, right, you want enough space so the bolt's not too close to the edge of the plate, because it'll tear out. Right, yeah, potentially tear out, right? So you added one here, but I actually think it's more important to add them here. Okay. You know what I'm saying?
Yeah.
The difference really is that those bolts are in shear, right? So if you imagine the downwards forces, it's causing the bolts to basically split apart through shearing. Whereas these ones, if you imagine a moment, so that's I-beam, and then you're connecting there, right? Pretend there's a moment that causes this, right? That's a plate, and you've got bolts like that, for example. This is inducing bending, right? And so the stress distribution actually looks like this.
Yep.
And so the top is going to want to pull out in tension. I'm just going to do it this way. Do you know what I'm saying? So that amount of tension is induced there.
Yep.
and then this one will be in compression. That much. Does that make sense? Yeah. So this is called out of plane bending of your bolts, which induces axial forces in these bolts. So that one's not really experiencing any. That one's in tension. That one's in compression.
So it extends further than the I-beam itself goes to the end of the plates. It's just straight, yeah.
Yes, because the plate itself is bending.
Yeah.
Yeah. Okay, let's go back to this whole thing, right? The way that I would detail it, all right, I'll draw it down here, okay? The way that I would detail this dashed line, and I zoom in, okay? So this is the top flange, okay, of your I-beam. The dashed line are the webs. Oh, sorry, is the web, okay? Now, this is your beam running north-south, or whatever, right? Now this web acts as a wall, okay? So we need a plate, an end plate, underneath it, right? Does that make sense? I might make this bigger.
So that plate's in between the flanges?
On either side.
Yeah, in between.
Oh, sorry. Yes,
Yeah.
yes, yes. I don't know what you're talking about, to be honest.
This one going through was one long beam. Like it wasn't split up in the middle.
Oh, it's split up here.
Yes.
Oh,
You were
I see what you're
saying
saying. But one of them has to be continuous and the other one's split up.
Yeah, well,
But then
maybe
how-
two continuous.
Oh, I get you. Okay. Sorry, I didn't know what you're saying. Yeah, so this one's continuous, but then this one has to end and then restart.
Yeah.
But how do you transfer the moments across, right? Right, so that's a bolt. Sorry, I should draw the bolt like dashed because it's underneath technically.
Yeah.
But there might be like 3 rows of bolts, right, underneath there. Okay. But this still allows for a bit of rotation. Okay. So you might imagine like that one's coming, and then if this bends, you've just got 2 pins basically, because I mean it's a little bit more pin than if this was a cleat, but it's got end plate, right? Oh, sorry. Like for full context. If I draw the section, like, if I draw, I don't want to draw the whole thing. If I draw like that, okay, where we're coping the flanges, and then the other one starts, then now we've got an end plate for the web. It's kind of trippy.
Seems a bit odd.
And then you bolt through like that. Does that make sense? Yeah. So you basically got a double cantilever thing, but it's still allowing a bit of rotation because these two things aren't connected together. But do you remember that very first, in week 4, Andy, how you suggested doing something at the top here?
Oh, yeah.
We actually do add a stitch plate at the top and bottom. And this will make it fully rigid, like connected together.
Yeah.
Okay.
I see. Because that stitch plate
Mm-hmm.
doesn't allow either of them to bend.
Separate from each other.
Yeah.
Exactly.
Yeah.
So what I haven't drawn, right, in this, it gets very detailed. Imagine all of that detail that you just saw, and then a stitch plate at the top, where you might go 1, 2, 1, 2 on both sides of the web, 1, 2, 1, 2, 1, 2, 3, 4, maybe. And you redraw the detail that I just rubbed out. Okay, it's a very hard detail, but hopefully that gives you an idea of the difference between moment connections and pin connections, right?
Mm-hmm.
And then hopefully, yeah, like if you look around and you see these kind of like, this is like a moment connection because it'll transfer all the moment across basically between these two beams or whatever. Yeah. Okay. I've just talked too much now, but yeah. Okay. I'm gonna stop recording. All right. Hello. I'm here in my home, and today we're gonna be talking about welds. Oh, sorry. Bolts and welds, so steel connections. So probably what you saw earlier in this video is just doing some demonstrations of what different connections look like. So I believe there was like the pin connection and the fixed connection like aka a moment connection. So it's good to see kind of the end goal of these two topics in terms of how like different members are connected together, right? So essentially when you're designing steel structures, right? Let's just say steel structures, you have kind of three components you're considering. You're considering the members, you're considering plates, and you're considering connections, okay? So with members, for example, let's just say an I-beam, okay? We've done all kinds of checks to these earlier in the term. We've done tension, compression, flexure, shear checks, all these kind of things. So you're checking it against all these different forces that are acting on the member due to the beam's loading scenario or whatever. Beam or column or whatever type of member, right? Or truss member. Plates are basically, for example, if you had, that's a good example. So you have two I-beams. It's not a really good example. Okay, but actually, that's a decent example. All right, so you have these two I-beams, and you want to connect them together because, for example, if you have a roof, right? So these are rafter beams on the top of a roof of a warehouse or something, right? Let's say that this warehouse is 30 meters wide, right? So the length of this beam has to be 30 meters essentially, right? Because these rafters are connected to columns, and it's partially fixed at these columns, the bending moment diagram actually looks like this. You can draw it like this. Okay. We have positive bending in the middle, and you have these negative hogging moments is what it's called. So negative bending moments at the columns, let's just say. And that's because these aren't actually pinned, they're partially rigid, right, at the columns. And so it absorbed this like moment, right? Typically where we have zero bending moment, these are called our inflection points. So it's basically where you have a zone where you're predicting effectively like zero bending moment, right? And these are good points to splice this member together, because a beam that's 30 meters long can't be delivered on a truck, because the truck itself, right? The truck itself, I'm gonna try to draw a truck. Okay. It can only really deliver members that are about 15 meters long, something in that ballpark. Okay, so you basically have to split up your beam, right? So if you were to split up your beam, you would split it up where you have zero bending moment, and so these connections aren't as being stressed as much, right? And you basically want to axially, you want to basically design your end plate to end plate connection with really strong bolts, so that the entire thing is able to carry these bending moments, right? So going back to the plates, right? How you might do a 3-plate splice. There's a few ways you can do it. The way that I see probably the most common is you have an end plate on both. So here's an example of a plate. Sorry, that's where I was trying to go, right? Specifically, this is an end plate because at the end of the member, right? So you have an end plate at both these I-beams, and you do a continuous fillet weld. Okay, so this is an example of where you might weld. So continuous just means all along it. Oh, wait, my video has not updated. One sec. Sorry about that, okay. Alright, sorry, so where were we? What I was trying to say is we've got these end plates, right? And you do this continuous fillet weld to basically attach the plate to the the beam, and then to attach the plates to each other on site, right? You would basically install these bolts such that they connect through to the other side. Yeah, like across like that. And you stitch these together, right? So, yeah, anyway, back to the connections, right? Which is the... I did a huge tangent, but like, what I'm trying to get at is today we're going to be talking about bolts, and we're going to be talking about welds, okay? So in this set of my notes, we're talking about bolts, and then like also in today's video, I'm going to be talking about welds, which is the week 9 set of notes, okay? So let's talk about bolts first, right? So essentially, there's two kind of forces that bolts are designed to take, shear and tension, right? So essentially, if you've got a bolt, let's say, and then you basically have it connecting two members together, two or more members, right? Where do I start with this? Okay, so if these two members, right, are pulling apart in tension, it basically puts the bolt into shear, like that, right? So you have to calculate the bolt's shear capacity in that case, right? And so this is, okay, in terms of like what everything's called, right? You've got the threads, you've got the shank, and yeah, and then usually you cap it off with a nut. So this is what you would use like a wrench or something like that to tighten these bolts, right? And you tighten the nut part of it. I'll talk about that a bit more later. So that's a shear connection. The other type is, probably I'll just use this example here. These are axial bolts, right? Because essentially, if this goes if this undergoes tension or compression, which we know is the case for a beam, right? So for a beam, say that's the bending moment diagram. Actually, let's go more simple, right? So we've got a simply supported beam, and then we know that it goes like that due to downwards forces. The stress distribution looks like that, right? So this is axial forces, and at the top we've got compression, at the bottom we have tension, okay? So let's just say that these bolts are being tensioned, right? And then these ones are being compressed, let's just say that, right? Either way, you have to design these bolts for tension because that's due to downwards loads, right? But imagine in your rafter, in your warehouse, there's a big gust of wind that goes into the building, and it basically increases the pressure inside the warehouse. Okay, so let's go through that again. You got a warehouse, you got like these, roller shutter doors. Probably be like over here. You got a big gust of wind that goes in. Okay, it increases the pressure inside the building, and so it wants to like balloon out. And what happens is you get upwards pressure on the roof. Okay, and therefore you get wind reversal. So instead of downwards forces, you get like this wind pressure that blows up, in which case you swap the tension and compression. So these bolts have to be designed for the tension case, essentially, right? Okay, yep, and then interaction between shear and tension together. There's a formula for that. Ply and bearing, I'll talk about that in a bit as well. Bolt groups. Okay, that's just like the interaction of when you have multiple bolts together. And then we've got some examples. Okay, so, all right, there's a bunch of terminology first, right? Yeah, okay, so where do I start? We've got the bolt grade, okay? So these are pretty common numbers, 4.6, 8.8. In this course, we won't do high strength bolts. We won't do 10.9. And the other thing to keep in mind is the method of tensioning, okay? So there's snug tight and fully tensioned bolts. And basically snug tight there's some kind of definition in AS 4100, but like it's just as tight as a human can get it with like a hand tool, like a wrench or something like that, right? Fully tensioned is basically you need some kind of machine that you put on, and it like how do you say it? It twists the bolt. Sorry, it twists the nut enough to basically yield the bolt. Okay. So the idea is if you torsion this enough, right? If you apply enough torque, the head and the nut of the bolt compress in to the material, right, of your plates, and it essentially tensions this bolt, right, like that. And then fully tensioning, you need to use that machine that basically torques this enough. Okay. Okay. So we use the ultimate strength of the bolts. So the bolts are designed to fail in like a brittle manner. So it's ultimate curve. So if you remember the steel material curve, right? For tension, oh sorry, I'll just draw it out first. Something like this, right? If you remember in tension design, sometimes like we have two failure modes to consider. We have the yield strength, and then we also have the ultimate strength, right? The idea is that for bolts, right, sometimes we actually want it to yield, okay, because it behaves in a ductile manner. So, for example, for the fully tensioned bolts, you actually want them to yield, so that they're basically unable to be loosened due to like cyclical loads. For example, like wind blowing on a building and then like there not being wind and then blowing again. It'll basically it'll loosen the bolts over time if it's just snug tight. Okay. So you actually, like in some cases you actually want it fully tensioned as to the point where the bolts yield, and then you're really designing for the ultimate failure point. So until the bolt snaps basically. So this is partially like the cross section's necked a bit due to the yielding. The failure point is once this bolt snaps open. Okay. Okay. Yep. So we've got like all the bolt shank diameters and whatever. Well, I think I have a good picture of it later. Yeah, I'll talk about it once I've got the good picture of it. But yeah, so we've got the core diameter and the shank diameter. Sorry, the shank area. And we've got the pitch. Okay, you know what, I'll just explain it now, okay? So that's the bolt. Okay, so so this is the shank, right? It's where you don't have the threads, right? And then the core is this thing. So the core has a smaller diameter than the shank because it's got the threads attached to it. So the threads are these things. And the pitch is the distance between these, okay? The distance between like a full 360 coil of the threads, basically. Okay, and then we've got, like, for the grade 10.9 bolts, we have, yeah, it's not in this course, basically. So basically, this table is associated with the 4.9 bolts. This table is associated with the 8.8 bolts, okay? All right, yeah, methods of installation. The only thing that I haven't talked about yet is bearing and friction joints. So essentially, if you've got, okay, how do I set this up? Let's go like that. Okay, so if you imagine the hole for these bolts to go into, right? The idea is that if you have a bearing joint, that means that the bolt just needs to, Okay, where, you know what I'll do? I'll draw, so the bolt has to be straight, right? And then I'll draw the hole in purple, right? So let's say that's being pulled that way, and that's being pulled that way. So that's two different plates being sheared against each other. The hole for the top plate has to be like that, and the hole for the second plate has to be like that. Okay, so that's void area. The idea is that it's the side of the bolt is bearing against the hole of the plate, right? Like here and here. So that's a bearing joint. Now, friction joint works a little different, and friction joints are generally where you require more tensioning. Okay, so you don't allow the plate to move against each other. So the idea is, let's say the hole and the bolt itself, right? We don't want them to touch each other. Okay, so let's just say they're like parallel to each other. The idea is if you tension this bolt enough, it essentially has to overcome friction in order to slide against each other, for there to be any slip between the two plates. So you'll see later in the table, if you remember from like Eng 1300, like friction, you have this, which is your coefficient of static friction. You'll see that come up. So that's the material property, which tells you how much basically like frictional, it's like a frictional constant basically, right? So the force of friction is equal to the normal force multiplied by this coefficient. That normal force in this context is how much you tension the bolts. Okay, so the more you tension them, the more friction that you have, right? Okay. As I briefly mentioned before, snug tight bolts, just like you've basically torqued them with a wrench or something, where you can't loosen them with your hand. For fully tensioned bolts, you just keep going, and it's not supposed to be able to be loosened properly, right? Like you really have to try to do it anyway. So when you're like inspecting bolts on a construction site, right? Like say you're a structural engineer and you're told to go on site and you have to inspect these bolts. Like it's very hard to tell how much it's been tensioned, right? Or how much they've torqued the bolt. And there used to be this like mark method essentially, where you put like you put a Sharpie on the nut and the bolt like that, and then you have to make sure they've achieved like a 60, what is this, 120 degrees rotation, right, between the starting point and like the final point. But now we have this method, which is do you know what like a Tide Pod is, right? Or just imagine like a dishwasher tablet thing. Just imagine that's placed in the washer, like underneath the washer, and when you tension it enough, and it's like way stronger, right? When you tension it enough, it just like shits out this like orange liquid, basically. So that's called a direct tension indicator. So if you see the orange liquid, the idea is that you've tensioned the bolt enough, right? Okay. It can also wash away in the rain though, so it depends on site conditions, etc. Okay, so bolts and shear have this formula. So yeah, the thing is we have these formulas and all that, but we also have this table. So this is like just common values that you'll see. Trying to think of like an example of what this is like compared to, like what you can compare this to from something you've seen earlier in your degree, but I don't really know an example off the top of your head. But basically, like say you want to figure out the shear of an M12 bolt, like that's grade 8.8 or something, for example, right? You can look at these values in the table, and it depends, like, sorry, so the value that includes threads is the bottom one, and then the bottom is if there's no threads. So for example, if you've got a bolt and that's the single shear situation, and the threads are down here. So the threads, like the smaller area, is not affecting your slip joint. Then you use the value for the top. Use the top value. No, other way around. Use the bottom value, the bigger value. But if the threads or the smaller diameter area intercepts where your shear plane is, then you have to use the smaller number. So yeah, that's basically how you read it. Now, you got to be careful because to use the table, you need to understand how the formula works first, right? The reason why it can be summarized in a table so easily is because a lot of the time these numbers are very, very similar. So for 8.8 bolts, right, we already know the value for your ultimate strength, right? But you need to know essentially like these ones. So sorry, that's a reduction factor for if you have a bolt 10.9 or more, but we don't have that. What probably matters more is the lap length, right? So imagine you have a lot of bolts in a row. Okay, so we're looking side on, for example, at a bolted connection. And you've got these two plates that are lapped together. And I'm going to draw a dashed line for the plate that's behind. Right, so we've got one plate that goes behind like that. We've got another plate that goes like that. The idea is, let's say we have a shitload of bolts. Something like that. Did I do an even amount? No. Okay. The lap length is pretty important because if your lap length from this first to the last bolt is 300 mil or less, you don't have to reduce your bolt capacity by any amount. But if it's between 300 to 1300, you basically have to modify this, right? So say it's 1,000, like a meter of these bolts overlapping, then you have to follow this formula basically. So you plug in 1,000 into this formula, and that will give you your KR factor. Yeah, and then so if you have the core area versus if you have the shank area, you get a different number, which is where the where this analogy that I was, or not analogy, this example that I was showing you comes from, and where these values in the table come from. The other thing is that you can have more than one shear plane. So for example, like this. Okay, so if you have 3 plates that are being stitched together, you basically have 2 shear planes, right? And so, yeah, you would probably look at the formula instead. So n is the number of shear planes, and it's the amount of shear planes with and without threads, right? So if you want to be conservative, you basically always take it as the core area, which is the smaller number, which is why I've written 0 here. But if you want to be accurate rather than conservative, you can, yeah. So I've got an example here that you can look at. So in this example, we have 1 shear plane where it intercepts the shank but not the core, and then 2 where it intercepts the core, or the threads, I guess you can say. Okay, so bolts and tension. This one's an even easier formula to understand, but it's very similar to the member tension thing. So it's the amount of steel that you have, like multiplied by the ultimate tensile strength, right? And you've got a reduction factor. Remember, your reduction factor for bolts and connections in this course are the only reduction factors that aren't 0.9. So whenever you're doing member reduction factors, it's always 0.9. For connections, you have to be a bit more careful, right? Yeah, there's like a table for it you can just read off of, okay? So these are, sorry. Yeah, you're looking at the tensile stress area basically in this table. And you're looking at, you know, the bolt ultimate strength, and you literally just plugging this into the formula. Or you can read off the table even, yeah. So in this table as well, yeah, keep in mind we have the slip modulus, right? The constant for static coefficient of friction, which I mentioned before. Yeah, so that's for your bearing joints. No, the other one. It's for your friction joints. Okay, bolts and tension and shear. This is very similar to the idea of when you had to look at shear and moment interaction together. So we're just checking that the combination of the shear acting on the bolt and the tension acting on the bolt doesn't exceed like this number basically. So you chuck in this formula. The idea is like let's get an example. Like, okay, so imagine like this is you, right? And you have uni, right? But you also have a full-time job, okay? So you're doing 3 subjects at uni, and you also have to work 5 days a week, okay? Like, so what I'm trying to say is you have a certain capacity for the amount of work that you can do, sorry, the amount of days you can work, but you also have a capacity for the amount of uni you can do in a given week, right? So these two like factors combined will overwhelm you, right? So the same thing happens with like bolts and tension and shear. Okay, ply and bearing. So ply is referring to like a plate or something where the ply material is actually getting destroyed. So you have to check basically the material that the bolt is connecting to, let's say a plate, to see if it will tear out or crush. Okay, so these are the 2 failure modes. So it's assuming the bolt isn't going to break, but the actual material adjacent to it will break. So this usually happens if I look top down, right? Let's just say it looks like that. And this is in tension, let's just say. The idea is if my bolt is too close to the edge of this material, it might tear out or crush or whatever. So crushing is like due to compression. Tear out's due to tension, essentially, right? Like that. Here I have a photo from work that is just like an example to show you. They basically had like in the roof of this warehouse. Oh, sorry, no, this is like a wall brace. They didn't line up the fucking hole properly for the brace and the plate that it's attaching to, and so they just drilled new holes next to the existing holes. And so there was this problem where there's like, so if you imagine the bolt actually has a hole here that it's like going through, and then the existing hole, right? You can see that the distance between these 2 holes is like pretty small, and so if you have a tension force that way, like it will just rip out, right? Because you basically have no like steel material that's like resisting this. Okay, so bolt groups are bolts like acting together essentially. And there's different examples. So in plane shear is like if we're looking at this beam as a column connection, right? In plane shear would be, for example, gravity loads or the reaction at the support. Because basically, like, sorry, all these bolts have to react essentially. It has a reaction force, like that. And that's like in plane shear basically. Now this can get more complicated if, for example, this beam is in torsion, because basically it'll make all these bolts do weird shit. But it's all like in plane shear that's causing it to break essentially, right? And there's all these formulas, right? So don't get overwhelmed. It's easier to see in an example. But it's just a matter of using the formulas and plugging it in properly. The other thing is if you have out of plane moments of tension. I don't believe this is in the course, but kind of similar to what I drew towards the start with the end plate to end plate splice connection. Imagine you have these 2 end plates, right? And then one of them's being bent or whatever, or both of them's being bent. essentially you can see the two plates are like bending out like that, or like prying apart. So the bolts, let's say there's like a big bolt that shoots through my hand, right? The idea is the bolt is like resisting it from tearing out like that, and therefore the bolt is in tension. So you have to check. That's like out of plane shear. Sorry, out of plane action, right? Which is essentially results in tension of the bolts. Okay, example 1, minimum bolt size. So, sorry, I'm probably not going to be able to run through all these examples, but it'd be good for you to just follow my working to figure it out. The reason is I've also got to talk about the welds as well. But yeah, so these are examples which are from 2023 when Hamid ran this course. So I'm not exactly sure how relevant this is now really to like taking the course this year. Okay, I feel like nowadays it's a lot easier than what you see for like connection design, because this is all like the in-plane action and you have these like weird moments and stuff. But I feel like Brian usually is pretty chill with it. Like he'll just do like so imagine there's no torsion on this beam. He usually just do the shear or something, for example, of a bolt group resisting like this force or something. Okay, that's bolts. Let's talk about welds, right? Okay, so welding, the first thing you need to know is that this capacity factor will change quite a bit, and you kind of need to know when. So the first thing is that, actually, yeah, okay, well, the first thing is the types of welds, right? So we have fillet and butt welds. These are the two broad categories of welds. A fillet is when you have two like perpendicular plates or surfaces that you want to weld together, and you end up doing this. Essentially, you have this like right angle triangle when you're looking at the cross section of it, that's welded on like to attach these plates together, right? So that's a fillet weld. And a butt weld is basically if you have two surfaces on the same plane, you basically have to carve out this little notch and then apply the welding material to fill in that gap, right? So that's a butt weld. Weld quality, the idea is in the code it's called general purpose welds or special purpose welds, but like essentially what this breaks down to is general purpose welds are if you sight weld, right, then the weld's like less reliable, so you apply like a lower safety factor to it. But oh sorry, not lower safety factor, like a lower capacity factor, right? And if you're welding in a shop, right, so you have like a workbench, it's the correct height, and like the welder's got a lot of control of the size of the weld and like how evenly the weld is being placed, then you're looking at special purpose welds, pretty much. That's the way that I interpret it, at least. And then this depends on the type of weld you've got. If you've got complete penetration or incomplete penetration is where you're butt welding to both sides, but you don't actually like go through the entire thing, and so like this middle bit isn't actually bonded together. And then fillet welds has the same number as well. Okay, cool. So so sometimes I'll specify an electrode, so it'll be like E41 for example. So E41 just corresponds to the weld strength, right? 41 means for 410 MPa for your weld strength, right? Ultimate weld strength. Okay, so when you apply a weld, let's say a fillet weld, right? And you want to weld these two things together, you do it in a few passes, so like along, so imagine, this is in 3D. So imagine you've got these two plates, right? You have to weld along the entire plate firstly, right? Like, you know, the longitudinal direction. And that looks like this, right? you do one pass and it might do that. You do a second pass and it'll look like that. Do a third pass, it'll look like that. Do a fourth pass, it looks like that. A fifth pass, and then a sixth pass, etc. So yeah, like the amount of passes depends on the throat thickness, basically, right? So you specify a throat thickness, and that's what all the design considerations are about. So this direction here is your throat of the weld, and the typical weld sizes that you specify for like not general purpose, that's going to get confusing with the term that I showed you earlier. In most scenarios, you either do a 6mm fillet weld or you do a 8mm fillet weld, and that's referring to the throat thickness. Essentially for smaller connections or like small to medium connections, you could do 6mm. For medium to larger connections, you do 8mm. You do more for even larger connections, right? Yeah, so TW is referring to like a single leg's length, which is this way. And then you can use trigonometry to figure out the throat thickness, right? Yeah, all this stuff's pretty straightforward. The idea is, yeah, you have like a minimum weld size that you have to follow due to the plate thickness, right? So if that plate is, let's say, 7mm, then, sorry, less than 7mm, then you have to at least have 3mm thickness. Max size, yeah, etc. Like this is just addition. Okay. So welds and shear are basically, you got these two plates in the weld together, right? Shearing of the weld would be like that and that. Okay. So yeah. Essentially, this strength is per unit length, right? So the longer your weld is, like the stronger it is. So if that weld is, let's say 500mm, so half a meter, you've got half a meter of welded like length, right? And then you'd calculate everything in terms of like that, right? But if you imagine instead that we only welded the middle, and instead of welding 500, you only welded like 50mm, right? You can see that there'd be like a linear decrease in the size, in the strength of the weld. So if you, instead of welding 500mm, you only welded 50, you'd have 10 times less strength, right, in your weld. Weld groups. It's similar to the bolt groups that you saw earlier, but you treat welds as like one-dimensional lines, right? And you want to find the centroid of these like one-dimensional lines instead of bolts being like a zero-dimensional point in space. An ICR is the centroid of center of rotation. Yeah, la-di-da, follow these formulas. Okay. Yep. Have fun coding all this shit. I've got examples so that you can just work through. Okay, so that's pretty much this whole topic. All right, thank you. That's my yap for today.